Hello, everyone, and welcome again to the MPAI Talks to Audio Industry. This is a third talk today, and I'm Marina Bozzi, the chair of the Context-Based Audio Enhancement Standard, MPAI CAE. And today I will present the work that we did in the past year or so. Basically, MPAI CAE aims to best experience audio. We are surrounded by sounds, and sounds are a very important part of our human experience. They can elicit a gamut of emotions, from distinguishing and warning us of imminent danger to basically the relaxation inspired by a gentle sound like a lullaby. But often, if we're trying to translate this into electric signal of audio, the experience can be inaccurate and, in fact, sometimes even distorted. So think, for example, something we're exposed today, probably more than we wish, the audio conference experience, where it is difficult to follow the thread of the discussion because either a noisy background environment or because multiple speakers talk at once. Or, for example, think about the emotionless voice and rapport with the robotic voice. What if we can make it more engaging by adding emotions? Or how can we preserve our cultural oral heritage for future generation to enjoy? How can we do that effectively? Or how can we enjoy music wherever we are? For example, we want to continue to be aware of any danger of the surroundings, but still we would like to have the option of listening to very high quality audio. So all this is something that inspired the work of MPAI CAE. And MPAI CAE aims to improve the user experience by using context information to act upon the audio content. And in doing so, we're addressing different scenarios, from example, in the home, in the car, on the go, or in the studio, and so on and so forth. And in this context, we identified 4 use cases, and these use cases are currently standardized in MPAI CAE Technical Specification version 1. They were finalized in December of 2021. So what are these 4 use cases? First of all, we start with the Emotion Enhanced Speech, EES, which enables the conversion of individual emotionless speech segments into segments that contain specified emotions. And this emotion can be expressed either as a tag selected from a predetermined list of emotions, or dynamically extracted from a model utterance. The second use case that we're going to be examining is the audio recording preservation use case, which enables the creation of a restored copy and an access copy of the digitized version of an open reel magnetic tape audio. And this is done in order to preserve in the long term, and also in order to have the correct playback of the analog information. The third use case we're going to be examining is the Speech Restoration System, SRS, which enables the restoration of a segment which can be damaged or completely missing of a digital vocal track by replacing it, completely resynthesizing it, based on a neural network model obtained from pristine parts of the vocal segment we're trying to reproduce. So the final, last but not least, certainly, use case I will be introducing is the Enhanced Audio Conference Experience, EAE use case, which enables an improved auditory experience by analyzing and transmitting not only the speech signals, but also the environment spatial attributes, and at the same time reducing, possibly distracting background noise. So let's start with the emotion enhanced speech use case, MPAI CAE EES. So as we all know, speech carries a wealth of information, not only about its lexical content, but also about several other aspects, including age, gender, identity, and most of all, the emotional state of the speaker. So the EES allows the conversion of an emotionless speech segment into one that has a selected emotion. So both the input and the output speech segments are contained in audio files, and we can add the emotion either by selecting from a list of emotions. So we're adding a label. For example, we select angry or fearful or any other emotion, or, and this is, I think, extremely interesting, by deriving the emotion from a model utterance from which we can extract the emotion speech feature. So this is an emotion of, sorry, this is a list of emotion categories that we standardized within MPAI CAE based on Paul Ekman publication of 1999, and we built upon that work. So how does this work? This is the MPAI CAE EES workflow, where basically we have two paths, one in the upper and medium part and the other one in the lower part. The upper part basically takes the model utterance and selects this emotion from the model and adds it to the emotionless speech. The lower part takes the emotionless speech and the emotion list and adds the selected emotion to the emotionless speech. And again, in both cases, we resynthesize the segment. So as I mentioned, there are two pathways for additional of emotional charge to the neutral utterance, the emotionless speech input. And in the upper and middle part of the workflow, which is a pathway one, we are taking the model utterance as input and as well as the emotionless speech. We capture the features of the model utterance, and then they are included, if you wish, in the emotionless speech. The pathway two, which is the middle and lower part of the workflow, includes the emotional speech as input, but also an emotion list where we specify the desired emotions. And the speech feature analyzer 2, this AIM, extracts the emotional speech features and describes the initial state of the neutral utterance. Finally, it sends this to the emotion feature producer, which produces a speech feature that will yield emotional charge specified by the emotion list. And finally, all this is sent to the last AIM, which is emotion inserter, which uses this information to synthesize the speech with emotion. So this is it for the first use case I wanted to present. Now we examining the second use case, which is the audio recording preservation use case, MPAI CAE ARP. So analog audio heritage is at risk. First of all, we can lose all this important information due to the degradation, the fact that we cannot read back what was encoded or recorded, I should say, in an analog way that cannot be easily reproduced. There may be large number of collections that require high costs, and in general, they have short life expectancy. So the solution here is to re-record the content in a digital format, but re-recording is not a neutral process. Errors can occur, and in addition, the access to these documents can be difficult because of the large amount of information we try to restore. So in general, the costs for preserving and accessing analog recordings are often not sustainable. So what do? We use artificial intelligence in order to drastically reduce the costs related to the analysis, the restoration, and preparation of the analog audio recordings. So in this particular case, we look at the specific case of the open reel magnetic tape. So this is the general workflow for the MPAI CAE ARP, where in input we have the preservation audio file, so the digitized version of the audio file, and as well as the audio-visual file, the preservation audio-visual file. And we're using the input in order to identify the errors occurred, and we identify them as irregularities. The irregularities can be identified both by the audio analyzer AIM and the video analyzer AIM, and then they are used in order to classify and select the different type of irregularities. These irregularities are then passed to the tape audio restoration, which restores, based on the irregularity types identified and selected, the original audio. And finally, the packager includes both the restored audio files and the editing list in order to have the excess copy files, as well as the preservation master files, where in addition we are including the irregularity file and irregularities images. So how does it work? We just saw it. We identifying the potential errors occurred during the re-recording, and we call them irregularities. And these irregularities are both audio, so identified by the audio analyzer, but also can be from the video of the tape, in which case are identified by the video analyzer. And these irregularities include the damages of the carrier, splices, marks, and so on and so forth. So the detected, irregularities are then classified and selected by AI algorithms in the tape irregularity classifier AIM, and are used to restore the audio signal. And this information is then packaged so that we have both copies for preserving and also accessing the open real recording content. So this is it for the ARP. I'm now describing the speech restoration system, the MPAI CAE SRS, which is somewhat, related to preservation, but here we are actually completely restoring missing segments of speech. So the problem is that the damaged or missing voice segments sometimes cannot be restored because traditional methods included filtering of extraneous noise or filling very minor gaps by extrapolating and interpolating the speech signal. What happens if the gap is major? What happens if the filtering doesn't yield results? So what can we do is actually completely replace the damaged segments. And the idea is that we learn from a model the relevant characteristics of the voice from pristine voice samples. Then by using a script, we regenerate based on the learned model, the damaged segment, and then fine tune if necessary. So in this particular case, the advantage is that we completely restore a large portion of missing signal. So this is the workflow for the MPAI CAE SRS, we start with the damage segment, the damage list in the segment, and the text list if we need to reproduce that. And then we also use pristine audio segments for modeling, where we create the speech model. And based on neural network speech modeling, we resynthesize the speech and assemble it with the damage list information. So the entire damage segment can be replaced by the synthesized segment, or in other cases, maybe only parts that need to be resynthesized. So we first use the AIM, the first AIM, to create the speech model, which is created by receiving a pristine audio segment for modeling. We are using all this to train and exploit neural network speech modeling, and we create a speech model based on the pristine segment. We then examine the speech model as well as the text list as an input so that we can recreate the damage segment. The speech synthesizer produces a synthetic replacement of each damaged sections or the entirety of the segment, and passes this to the assembler. The assembler receives the damage segment plus the damage list and restores the segment that was missing or heavily damaged. So this is it for the SRS use case. We now are describing the enhanced audio conference experience, MPAI CAE EAE. So typically audio conferencing aims to transmit speech by using one single channel microphone. And when necessary, if the noise of the background environment is too high, we can filter out extraneous noise. But if the environment contains multiple speakers and disturbing noise, highly disturbing noise, sometimes it becomes almost impossible to follow the discussion. So what do we propose? We propose to use, instead of a single audio channel microphone arrays for the audio conference, so that we can detect the location of the speech sources. We can separate the speech sources by using the location, and also we can act upon the noise environment by denoising it and maybe correcting some of the reverberation, which is this disturbing intelligibility. And finally, we package the speech sources with their spatial information to transmit. So not only the audio signal is transmitted, but also the spatial information. So the advantage by doing that is that we can render multiple speaker and noise environment suitable for very, very clear audio conferences. So we're improving the experience. So how does it work? We process the signals from a microphone array to capture a complex description of the sound field in the spherical harmonic domain. We process this spatial information to detect and separate different speakers. Finally, we estimate the number and the directions of the speakers in the room, and we reduce or possibly completely eliminate the background noise and the reverberation in order to enhance the quality and intelligibility of the speech, of the conversation. Finally, we package the speech signals as well as their spatial attributes for reconstruction at the receiver side, and so we're enhancing the overall audio conference experience. So this is a block diagram of the MPAI CAE EAE workflow, and it's sort of complex. As you can see, there are 6 distinct AIMs, AI modules. We start with the analysis of the microphone array audio. In addition, we also have an input at microphone array geometry. So we're looking at the microphone array multi-channel audio in the transformer domain, typically the frequency domain. Based on the microphone array geometry, we are describing the sound field in terms of spherical harmonics decomposition. And based on that, we can detect and separate the different speech signals. The spherical harmonic decomposition, along with the speech and audio scene geometry, is utilized to denoise the overall signal. And finally, we resynthesize the denoise speech, and together with the audio scene geometry information and the microphone array information is we are packaging all this information so that it's transmitted to the receiver side of the audio conference experience. So this is it for MPAI CAE technical specification version 1, but I would like to go over what we are cooking for the next version 2. And that is that we are looking now specifically at one standalone use case, which is audio on the go. And the idea is that we want to improve the sound quality when we are on the go, but we still want to be in touch with the content of the acoustic surrounding. In case we're in danger, we want to react. So this is the workflow for the general workflow for the AOG use case, which again will be part of MPAI CAE version 2 technical specification. In input, we have transport info, geometry info, and microphone sound information. And we act upon the sound signal by separating the different components. So we have the speech signal as well as geometry information. And we are processing the environmental sound so that we can extract the relevant sound that we want to be aware of and ignore the ones that are not necessarily important for our experience, both in terms of high quality audio and imminent danger that we need to be aware of. Finally, in the dynamic signal equalization AAM, we are using the user hearing profile information in order to equalize the sounds for the best ultimate experience. And finally, the dynamically equalized speech or audio is delivered along with the transport information. So this is it in terms of the work that we have done so far in MPAI CAE. And again, we are aiming to improve the user experience by adopting the contact information to act on the audio content. For MPAI CAE technical specifications version 1, we have identified 4 use cases and standardized them. And they are the emotion enhanced speech use case, the ARP use case, the SRS and EAE use case. So all these constitutes technical specification version 1 of MPAI CAE, but we're also working on MPAI CAE technical specification version 2. You can find all this information by looking at our website at cae.mpai.community. So I encourage you to do so if you want to know more about the details, about more technical specifications for the MPAI CAE standard. And finally, I wanted to thank you for your attention, and I look forward to continue this conversation